Alright everybody, today should be a pretty short video. I'm sorry that this PowerPoint is not showing up very well, but what we're looking at is we're finishing up chapter 15 on glycolysis by looking at the metabolism of other hexoses or sugars that is commonly seen in the body, as well as the pentose phosphate pathway or PPP, which is a pathway used to derive another one of our powerful reducing agents in biosynthesis, NADPH. And the reason we talk about the pentose phosphate pathway in glycolysis is because we utilize glucose 6-phosphate in the pentose phosphate pathway. All right, so here are our learning objectives. They're pretty short and sweet, so take a moment to print these out and read these over before we continue on in the video so that you can have these ideas in the back of your mind. So, for this whole time when we were talking about glycolysis, we were talking mostly about the metabolism of glucose. But as you know, we often intake other sugars or hexoses that can be utilized in glycolysis. So fructose, galactose, and mannose can all be converted to glycotic intermediates and used. So as you see, galactose can be converted to G6P. Mannose and fructose can both be converted to fructose 6-phosphate. This being in the muscles for fructose, you'll find that the liver and the muscle metabolize fructose differently. So in the liver, when we metabolize fructose, it becomes glycerolaldehyde phosphate, or GAP. So if you remember when we were talking about disaccharides, we can get galactose when we ingest milk or lactose. Sucrose is a dimer of glucose and fructose, so whenever we eat sugar that is sucrose, we're able to metabolize both the glucose and the fructose. We also can, maltose is glucose-glucose, cellulose is glucose-glucose, but we can't digest cellulose. Okay? Mannose is a less commonly encountered sugar. Usually it's encountered as a monosaccharide. Every now and then you can get a disaccharide of 2 mannoses, but it's not as common as, say, the lactose or sucrose or high fructose corn syrup, which are common in the U.S. as a sweetener. Okay, we'll talk about that in a minute. So fructose is metabolized differently in the liver than it is in the muscle cells. So if we look, so here is glycolysis. Starting with glycogen, or if we cleave a glucose molecule off of glycogen, so basically you could substitute glucose here. If we look on down, here we have fructose. Okay, well I guess glucose starts here in glycolysis. We can talk about glycogen metabolism in the next chapter, but for what we have studied on glycolysis, we have been starting here with glucose being converted to glucose 6-phosphate, and then we have an isomerase reaction of fructose 6-phosphate. So if we're starting with fructose, all we have to do is add a phosphate group using another hexokinase to make fructose 6-phosphate. So this hexokinase is the same hexokinase that converts glucose to glucose 6-phosphate. So both hexokinases can phosphorylate fructose glucose as well as mannose in muscle cells. But however, remember we have a different kinase in the liver, and it cannot bind and phosphorylate fructose. So in the liver, right here, fructose gets phosphorylated by fructokinase instead of just hexokinase to make fructose 1-phosphate. Then we have an aldolase reaction that will create DHAP and glycerolaldehyde. And then glycerolaldehyde kinase will phosphorylate it to make the glycerolaldehyde 3-phosphate. All right, so instead of making DHAP and glycerolaldehyde 3-phosphate from fructose 1,6-bisphosphate, we're making it directly from the fructose 1,6-phosphate. Okay, and we'll talk about why this is sort of an important piece of information. So in the liver, fructose gets converted directly to GAP here, where in the muscle cell, fructose first gets converted to fructose 6-phosphate and then uses PFK1. So here we have the enzyme PFK to make the fructose 1,6-bisphosphate. Again, mannose is pretty easy. It's just the same hexokinase that phosphorylates glucose will phosphorylate mannose. Then we have a isomerase reaction to convert the mannose 6-phosphate to fructose 6-phosphate. So in fructose metabolism, remember how I said in the liver we bypass PFK1? Well, if you remember, PFK1 is a big control center for glycolysis. So by bypassing this major point of metabolic control, if we have a high excess of fructose in the liver due to the use of high fructose corn syrup, we can bypass PF1 control, which leads to an increase in lipid synthesis, right? So all of our fructose is getting converted into ATP. We get an overabundance of ATP, and we have less control of this glycolytic pathway, so any glucose or excess fructose that we have in the system, instead of being shuttled into different pathways, gets shuttled into lipid synthesis. And then what that happens is it's going to cause liver damage due to fatty liver. So when you saw those commercials, that was trying to be a proponent of high fructose corn syrup, the commercial always said that our body does not process fructose differently than glucose, and that's completely untrue. The liver processes fructose completely different in the liver tissue than the muscle tissue. Galactose metabolism occurs by converting galactose to glucose 6-phosphate, but it requires a 4-step process. So it's not as direct as it is with mannose and fructose in the muscle cell. So galactose gets phosphorylated to galactose 1-phosphate. Then we have to do a transferase to transfer uridyl or UDP from UDP glucose to UDP galactose, and then we have an isomerization to get UDP glucose, and then we end up dephosphorylating. So UDP glucose to UDP galactose, then we can have an isomerization reaction to make UDP glucose. It's sort of cyclic here, doesn't it? Looking. And so eventually we get to glucose 1-phosphate. Now, interestingly, there's a disorder, it's a genetic disorder called galactosemia, in which patients are deficient in the enzyme galactose 1-phosphate uridyl transferase. So this enzyme here becomes deficient. So the cell doesn't produce as much as it should in order to convert galactose to glucose 1-phosphate. So what happens is we get a buildup of galactose 1-phosphate in the cell, and this causes failure to thrive, mental retardation, and liver damage that can lead to death. So normally treatment for these patients is to avoid any galactose in your diet, and this can reverse some of the symptoms of the disease, such as the failure to thrive and liver damage. However, it cannot reverse the mental retardation once that has happened. So now let's kind of change gears, and we're going to finish up this last section of our chapter, which is the pentose phosphate pathway. The pentose phosphate pathway is used to develop NADPH. So this is not to be confused with NADH. All right, so NADPH is a high energy molecule that utilizes reducing power. So this is another one of those reduction oxidizing mediating cofactors for enzymes to aid in biosynthesis. So NADH, so again, not to be confused with NADH, because NADH utilizes the free energy of metabolite oxidation to synthesize ATP, such as we'll see in the electron transport chain, while NADPH is utilized for reductive biosynthesis, so creating biomolecules. So NADH is for creating ATP, while NADPH is used for creating biomolecules. And we can see the cell keeps the NADH ratio, I believe, at about 1,000 times that of the NAD-pH ratio. So NAD-pH is generated using glucose 6-phosphate through the PPP, or the pentose phosphate pathway. And oxidation of glucose 6-phosphate through PPP versus glycolysis is commonly seen in tissues that do a lot of lipid synthesis. So with liver, mammary glands, adipose tissue, and adrenal cortex, we see that more often than not, glucose 6-phosphate is used in the PPP pathway versus going straight to glycolysis. Now, the byproducts of the PPP pathway we see is fructose 2,6-phosphate. Is fructose 6-phosphate as well as GAP, which are both intermediates in glycolysis. So we can still use the G6P that we shuttle through the pentose phosphate pathway. Eventually, it will still return to glycolysis through these intermediates. However, we also get the advantage of generating some NADPH when the cell needs the NADPH. So the PPP can be divided into 3 basic stages. So stage 1, we have oxidation reactions. This is what yields our NADPH, as well as ribulose 5-phosphate, or R5P. And we'll talk about the importance of that in just a minute. Stage 2, we get isomerization and epimerization reactions, which are steps 4 and 5. This transforms R5P to ribose 5-phosphate or xylulose 5-phosphate. So I guess that's not R5P, this is RU5P. Okay. In stage 3, a series of carbon-carbon bond cleavage and formation reactions, which are steps 6 through 8, convert the 2 molecules of xylulose 5-phosphate, so the product of stage 2, and 1 molecule of R5P, again stage 2, to 2 molecules of fructose 6-phosphate and 1 molecule of GAP. So again, remember, these are our intermediates in glycolysis. Stages 2 and 3 are freely reversible, where stage 1, we control the enzyme. So in stage 1, this is an irreversible process. G6P, so remember this is that first metabolite after glucose gets phosphorylated in glycolysis, is then undergoes a oxidation reduction reaction to become 6-phosphoglucanolactone. And we see that we generate an NADPH. In steps 2 and 3, we get the formation of the ribulose 5-phosphate, or RU5P. For each molecule of glucose 6-phosphate that enters the PPP, we get 2 moles of NADPH. So you see here we generate another NADPH at this stage. We also see we generate some CO2 as well. So this is 2 steps, right? So the 6-phosphoglucanate is further goes through another oxidation reduction reaction to create an keto acid intermediate, and then we do a decarboxylation reaction to get the RU5P product. Stage 2, which is steps 4 and 5, is where we, so that's this step here. All right, so we take ribulose 5-phosphate and we convert it to either ribose 5-phosphate or xylulose 5-phosphate. So both of these enzymes are present and can be controlled by the cell in which isomerase we are forming. So in rapidly dividing cells where DNA synthesis is in high demand, R5P production is much higher because R5P is a precursor in nucleotide biosynthesis. So if we need, say we're undergoing DNA replication, cellular replication, the R5P will then be shuttled off for DNA synthesis, and therefore if we're removing R5P in the equilibrium for other steps in the reaction, then obviously the product formation of the R5P will be enhanced versus the xylulose. However, if PPP is used primarily for NADPH production, the xylulose 5-phosphate is preferred about 2 times as much as the R5P. So without the need for DNA synthesis, we'll see that this isomerase reaction is preferred over the R5P. In step 6, this is the beginning of stage 3, a C2 carbon or a 2-carbon unit is transferred from xylulose 5-phosphate to R5P to yield GAP and a molecule called S7P. Okay, so this is a transferase reaction. In step 7, a C3 unit from S7P is then transferred to GAP to give us a erythrose 4-phosphate and then a molecule of fructose 6-phosphate. In step 8, a C2 unit of a second molecule of ZU5P, so this is sort of why we need that 2-to-1 ratio of the XU5P versus the R5P that we saw here. So another C2 is transferred to erythrose 4-phosphate, which gives us another molecule of GAP and another molecule of fructose 6-phosphate. So in the end, our principal products of PPP are NADPH and R5P. So if we are undergoing nucleotide synthesis, R5P will be shuttled off. However, if there is no need for nucleotide synthesis, then R5P and XU5P will be used to make fructose 6-phosphate and GAP. And then again, remember, we're producing NADPH throughout this. This is the whole point of the pentose phosphate pathway, is to produce NADPH. So flux through the PPP pathway is controlled by the rate of G6P dehydrogenase, so the enzyme that controls this step. G6P dehydrogenase is activated by NADP+ and inhibited by NADPH. So NADPH inhibiting this enzyme is an example of a feedback inhibitor. G6P dehydrogenase expression in the cell also seems to be controlled by hormones, possibly. You can find more about this in box 15.4. I believe that's how it is in my chapter, in my textbook. So it may be a different box number for yours, but you can read more about how the cell can control the expression of this enzyme to begin with in order to control pentose phosphate pathway flux. All right, so I believe that's everything. Yeah, for this chapter. I will see you in class Monday. And again, remember, there's still some students who hadn't taken exam 2. So please remember to try not to talk about the exam with each other until after those students have taken it. And I will see you in class Monday to start our next POGIL assignment. Okay? Hope you guys have a fabulous weekend. Where did my thing go? Here we go. All right.